So now we'll see how to do band pass filter. Suppose you have a source Vs and here you have a inductor, capacitor and resistor here C L. Okay, and here I'm taking the output across the R. So this question also came in CSIR net. The circuit they are given and they asked what kind of filter it is. So this is basically your band pass filter. And now if I want to write the output here, so output I'm taking across R. So it will be R divided by total resistance. Total resistance will be what? R plus XL plus XC plus XC. Okay. And now N2 Vs or V input, whatever you want to write. V input, if you write here, V input. So gain will be what? V input divided by V output by V input R upon R plus this will be your J omega L and this will be 1 plus J omega C. So the gain can be written as R upon R plus J common omega L. Okay, I'm taking J common, the J square minus 1 by omega C minus 1 by omega C. This is the function of gain and the amplitude कैसे लिख देंगे? एम्पलीट्यूड हो जाएगा आर प्लस आर स्क्वायर प्लस ओमेगा एल माइनस ओमेगा सी का स्क्वायर अंडर रूट. This is the formula for magnitude. Now if I check this one, okay, if XL is equal to XC, that is omega L is equal to omega C, say some frequency omega naught, then at frequency omega square equal to under root LC, omega square under root LC, what will become? This gain will become 1. This gain is 1. Okay, and now if you see at what happened to 0 or infinite frequencies, some frequency equal to this frequency, the gain is 1. And now we'll see other frequencies, say omega 0. So omega 0 means, tell me, at omega tends to 0, a omega is equal to, tell me what is the value of a omega. If it is 0, this becomes 0. If it is 0, it is infinite divided by 0. So a omega will become 0. Similarly, when omega tends to infinite, okay, omega tends to infinite, if you take omega common, this will be L minus 1 upon omega square C. If omega is infinite, this becomes 0. This omega infinite. So what will happen? If infinite, this also again will become 0. So if you plot the graph a omega versus frequency, okay, this graph will approach like this. At some frequency omega naught equal to L by root C, the gain will be 1. and before that gain will be like this. Okay, and this will be the cutoff frequency. These will be the cutoff frequencies where your gain is 1 by root 2 of 1 by root 2 of uh, 1 by root 2 of this gain of this frequency. This will be 0.707. So this frequency is your omega 1 and this frequency is your omega 2, and this is your omega naught. This is the width. Okay, so this is the band pass filter. So you just have to remember the circuit. Now, ideal band pass filter is what? Ideal band pass filter is this one. Is ideal. So if you take the log or gain, then it will look like almost like this. This is the ideal curve. So this is a band pass filter. Now next is band reject filter. Next is your band reject filter. Okay. So I am erasing this one. If anybody has not written, so you have V input, you have R here, this is your L, this is your C, and now you're taking the B output here. This is band reject filter circuit. Passive filters we are doing, and now V naught by V input, A frequency of gain will be what? It will be J omega L minus 1 upon omega C XL J omega C. So I'm taking J common. So this will be omega L 1 by omega C, and total will be what? Total will be R plus J omega L minus 1 upon omega C. This is your gain. Now you can check this gain again. If omega L equals to omega C, that is at frequency omega naught square equal to 1 by LC. Okay, this omega L equal to omega C. So your A omega will become 0. That is whenever XL equal to XC, this becomes 0. And if you say my omega tends to 0, okay, if I say omega tends to 0, then what will happen? If I take omega common here, okay, if this kind tends to 0, everything is 0, and let us write in different way. Let me write this as a, say I'm writing here, I am taking 1 by omega c common, omega c common. So this will become omega square LC minus 1, omega c is common. Similarly, bottom will be what? R omega c, R omega c plus J omega square LC minus 1. Can I write like this? Omega c is there, omega c cancel. Now if you put omega 0, this 0, this 0, this minus 1, okay, and this is also minus 1, so your a omega will become 1. Similarly, if I take omega equals to infinite, then what will become? So for omega solving, this same expression also I can write like this also. So I can take omega L common, and then I can write 1 minus omega square LC, omega L common. Okay, similarly here, bottom also omega L common, so this will be R upon omega L, omega L common, omega L, omega L, omega will be cancelled out. So this will be R plus omega L plus J 1 minus omega square LC. Like this also I can write. Now if omega is infinite, this become 1, this becomes 0, okay, and this become also what? 0, so JJ cancel, so again a omega comes out 1. So at a particular frequency it is 1 approaching 1. When it's approaching this one, this is approaching 0, this is approaching 0, and all other places it is 1. Okay, now let me plot the graph. If I plot this graph will come, it is 0, it is 0 only at omega frequency, it is 0 only omega naught. Okay, here 0.707, this is 1, other frequency it is 1. Okay, and if you want to make it ideal, so ideal will be what? Ideal will be, this is ideal. So this is your, this band, and this frequency will be omega 1 and omega 2 again. Okay, so this is the band reject filter. So only you have to remember the circuits. Sometimes directly circuit is given and they'll ask you what kind of filter is this. Okay, now we'll use op amp. Okay, we'll involve the op amp and we'll find different kind of filters. We'll use different kind of filters. Let me start with a low pass active filter. These were passive filter. Now let me start active filters. Active filter, first I use low pass filter. Active filter means using op amp. So first is low pass filter. Again, I use inverting configuration. Sorry, negative feedback. So you have here, say R. Say here you have a RF. Here I'm taking V naught. So this is the low pass filter in non-inverting configuration. I am applying input as non-inverting. This will be ground. Non-inverting configuration. Now I am giving input here. Say here one resistance is there. Is a low pass. Okay. So this is grounded, and here I'm giving some V input. So this circuit will work as a low pass filter. Low pass filter. Now you can easily judge if a circuit is given without solving the gain formula. You can tell easily whether this is a low pass filter or high pass filter. How? Say if the signal is of high frequency, say V infinite. If the signal is of high frequency, V infinite, then what is the drop here? Can anyone tell me what is the drop here? If the signal is high frequency, what is the drop here? It will be low or high. What is the value? What is the impedance of reactance? 1 upon
omega c.
So if omega is infinite, this becomes
हो जाएगा
जीरो. तो
Zero.
यहाँ पर क्या आएगा? जीरो हो जाएगा. तो गेन यहाँ क्या हो जाएगा? जीरो हो जाएगा. इसका मतलब ये सर्किट, दिस सर्किट विल नॉट पास हाई frequency. This will pass only low frequency. That is called lowest power filter. Okay, as the frequency become high, this voltage will become zero. So this is a non-inverting configuration. The formula is 1 plus RF by R into V plus V plus 0. Okay, so you can directly say if omega tends to 0 infinite, V plus tends to 0, and V plus tends to 0 implies V naught is equals to 0. So this is not passing high frequency. So this is will act as a low pass filter. If it's zero frequency, this will be very high. This will be DC. This will be open. So that this voltage directly will come here. So we'll get the highest gain. Okay. So if it is if omega is zero, DC frequency, then what will happen? This is infinite, open, and here no current flows. So this V plus will be equal to directly V input, and V naught will be what? V naught will be directly your 1 plus RF by R into V plus or V input. So this is a direct check, but we can calculate the expression. And this filter, what I am discussing here, they all are first order filters. Now, what is first order? We'll discuss first order filter circuits. Now, let me write the gain for a V naught expression for this circuit. So V naught will be what? V naught will be 1 plus RF by R into V plus. And now V plus is what? V plus is here voltage, that is 1 by j omega c upon R1 plus 1 by j omega c into this V input voltage division here plus here. This is voltage division. And now if you solve this one, V plus, this will cancel out and you'll get 1 upon 1 1 upon 1 plus j omega c r1. Omega c r1. If you want, you can put it to c1 also, no issue. If you want, you can put it one capacitor is there, 2 is there, so it's in c1 c2. So this you can put c here into v input. Now put this v plus value here. That will give you the gain expression. Now, if I write V naught, so V naught will be what? V naught will be 1 plus RF upon R, and this is V plus, this will be V input 1 plus J omega C R1. Okay. So I can write V naught by V input, which is the gain, equal to 1 plus RF by R 1 plus J omega C R1. Now, if omega tends to 0, your gain at omega 0 frequency, I write as a DC gain, or I write as A0 or ADC. You can write A0 ADC, which will be equal to now 1 plus RF upon R. If I put 0 here, gain at 0 frequency will be A naught, which is 1 plus RF by R. So now this expression of gain also can be written as a naught. Instead of this one, I am writing this A naught 1 plus J omega C R1. Okay. Now what you can write? So this expression we have already seen. If I define a cutoff frequency 1 plus J omega upon omega C, okay, where omega C is what? 1 upon C R1. So I can write this expression like this, okay, and okay. So what you're writing? Expression for gain, and we already know this is your low pass filter, because if I write this one, A naught magnitude will be 1 plus omega upon omega C square. Correct ना? Am I doing a mistake? यही फॉर्मूला था पिछली बार भी, अंडर रूट. Okay. So this the gain formula is what? 1 plus omega upon omega c square, or A naught 1 plus f upon fc square. Okay, and this formula is what? This formula is basically of low pass filter, because if omega is infinite, okay, omega is infinite, gain magnitude is 0, and 0 pe we have already seen the gain is A naught, and we don't know what is A naught value, this one. Okay, so this is a filter, low pass filter. Now I want to discuss some more things here. Why it is called first order circuit? Okay, so so this is my formula for gain. Okay, now I want to write this gain in terms of dB. Okay, so let it write now gain as dB. Just give me 1 minute. So say I have expression, this expression of gain. I'm writing it out again. A omega A naught, okay, 1 plus f upon fc square under root. Okay, now let us say that my A naught value is 10 raised to power 6. It is given to me. Okay, and my cutoff frequency fc, which I defined, I can choose my R and C such that my fc value is 5 hertz. It is defined in such a way. Now let us see what happens. Now if I want to write the gain in dB, so I have to take the log 20 log 10 of mod of this one. Okay, mod of AW, and this can be written into the 20 log 10. Okay, I can write this as a mod of A naught minus 20 log 10 mod of 1 plus f upon fc square. I can write like this, and this is my dB. Now see, let us what happens when my frequency is 0 hertz. If frequency is 0 hertz, I put 0 here. This become log 1. Log 1 is 0. So my gain becomes, okay, gain becomes how much? 20 log 10. This is my 10 raised to power 6. So my gain becomes 120 dB at 0 frequency. Now, if I say my frequency is FC, that is 5 hertz, okay, then what will become? My A omega will be what? It will be 20 log 10 raised to power 6 minus 20. Okay, so this FC will become how much? Tell me. 1. So this become root 2. So this become log 10
Log 10 root 2.
root 2. This is 120 dB. 120. And what is the value of this one? Tell me.
So 0.707.
No, 20 also there ना. log 10. log 2 की वैल्यू क्या है? पावर हाफ इधर भेज दो. 10 log 2. So half will come 10. 10 into 0 point is almost 3 dB. Check it. So this will
Yes,
remain.
sir.
This will
Ye-
come 1117 dB. So now here we are getting new definition of cutoff frequency. Earlier we say, earlier when the gain was in number, we told that cutoff frequency is the frequency at which the gain reduces by 1 by root 2 or remains 0.707. Now I am defining a new definition of frequency. Okay. So cutoff frequency F equal to Fc is the frequency at which gain reduces by minus 3 dB or loss by 3 dB. So minus 3 dB frequency is called cutoff frequency. Minus 3 dB frequency, यहाँ पे loss 3 dB का loss हो रहा है, which is called your cutoff frequency. ये definition है dB में. सेम थिंग है नंबर में. नंबर में अगर 1 बाई रूट 2 है 0.70 रह जाता है तो डीबी में वो 3 dB से डिक्रीज हो जाएगा. Because filter we generally represent numbers in the dB, so here this definition will be useful. Now we have values. Okay, remember these values 120, 117. Now what I'll do, I'll keep on increasing frequency because this is a low pass filter and it will start reducing. I'm erasing this one definition. The cutoff frequency is the frequency at which gain reduces by minus 3 dB. Now let us say I increase my frequency by 10 multiple of cutoff frequency. That is now my frequency is say 50 hertz. Okay, that means 10 time of FC. So now my gain will become what? Gain will become, this is 120, this is fixed 120 minus this value will be what? This is 10 FC upon FC, 10 into 10, 100. 1 we can neglect, 100 means 10, log 10, 10, log 1. So this will be, so it will become how much?
20.
20. So my gain will become 100 dB. Now you say you reduce the new thing. Now you say my frequency is say 10 multiplied say 500 hertz. Okay. Now tell me what is the gain? So gain will become dB. This is remain 120 and this is 20. This is 100 time of FC. So this is 10 to the power 4. Okay.
10,000.
So 100 will come only. 100 will come na.
Yes, sir.
So log 10 is 1. 2 power come here only 40. So it will remain now 80 dB. 80 dB. So gain is reducing by 20 dB. I started with cutoff after cutoff frequency. For each increase in when I'm increasing by frequency by decade, my the gain drops by 20 dB. Now you can check one more. If say f equal to 5 kilohertz, that's 5000, and then my gain will become dB. Everything is in log. Okay, so this will become what? This will become 120 minus 60, because 1000. If you solve this one, it will come 1000, 3 power 60, log 10 1, 60. Again, this becomes 60 dB. So the drop is by 20 dB. Now you can keep on increasing by 10 kilohertz. If you use f equals to 50 kilohertz, then my gain will become dB. How much will become? 120. हाँ बोलो.
40 dB आएगा.
40, 80, 40 dB. So gain will be keep on reducing. And now if my frequency is 1 megahertz, or say 5 megahertz, if my frequency is 5 megahertz, then tell me what is the gain? 120 minus, this is 10 raised to power 6. 10 raised to power 6, 6, 120, 0.
0.
120, oh yes, 0, 0 dB. So now let me plot this curve and see what information we get. So now if I plot the gain in dB, that is log scale, okay, and I take frequency also at a log frequency, okay, log of frequency, and if I plot this graph, what happens? Initially, this is my gain at 0 frequency, 10 to the power 6, it is 120 dB, na? 120, around 120 dB. 120 dB. And then it is reduces slightly at frequency equal to cutoff frequency. Cutoff frequency is log scale, okay? Understand log scale. This reduces by 117 dB, that is minus 3 dB loss. So graph is, if it is a graph is given, then it is the original initial gain, and you reduce by minus 3 dB. That frequency will be your cutoff frequency. You can directly write from the graph. So this is cutoff frequency. Of course, log here. This is a log scale. Sometime it will be number. It may be draw numbers. Then this drop will be fast. Okay. Now, if I want to show what happens after if I increase by decade, so this will go down with a constant slope. Okay. That is, this slope will be minus 20 dB per decade, and increase in frequency. Okay, after cutoff frequency, this circuit gives gain 120, then this is 120. Cutoff frequency this 10 times. These become 100, 80, 60. Constant rate it is getting down, and the drop is decreases minus 20 dB. So this is called first order circuit. Whenever the drop is minus dB per decade, that is your first order circuit. Now if this is a 40 dB per decade, then it is called second order circuit. And like this, you can keep on moving. So if you use, instead of one branch, one capacitor, two capacitors, then the drop then you can reduce this drop very fast. So basically you have only this kind of gain. Is this you have a, so not this one, this one gain. This is the ideal low pass filter. So before cutoff frequency, low pass filter, low frequency will pass and everything becomes zero. If you increase the order of the circuit, this is second order, minus 40 dB per decade. Similarly, minus 60 dB per decade, then this drop will be faster and you'll get only this curve. Higher order circuits, only you get this curve, and which is low pass filter, but we are only seeing the elementary circuit. We are not going for higher order circuits, but actually practically you use higher order circuits to get this low pass filter. Okay. Now let me do one more low pass filter. This is a non-inverting configuration. Same low pass filter we can make in inverting configuration. Okay, so put the heading now, inverting configuration.
Excuse me, sir.
Huh.
So there is one confusion that why we consider here the log f instead of f only, because we just vary the values of f only. And
But
no,
but if when you plot the graph, okay, if you want this straight line graph, okay, because what we are taking number is what, first I'm taking 5 hertz, then I'm taking 50 hertz, and then if I'm taking 500 hertz, so these number I cannot show here, na? The scale will not be linear, na?
okay, sir, okay.
So
Get
that's
me,
why
sir,
I'm
get
taking
me.
log. That's why I'm taking log. So this should become in smaller
Yes, sir,
scale.
yes, sir.
Okay.
Very clear, sir. Thank you, sir.
Hmm. So let us now use inverting configuration. So inverting means now I have to make this ground. Okay. And here say is R, and here this is R1, and here is a capacitor C. I'm taking a parallel combination of R1 and C, RF and C. Okay. RF and say C1 or C whatever. Here you're applying V input, and here say I'm taking V naught. Okay. Tell me what is the gain formula? What is the gain formula? Calculate. First of all, you can directly check whether it is a low pass and high pass. Kaise? If the gain of this now this is your what? This is your ZF. So now so V naught will be what? Now this R and C. Okay. This is a parallel combination. Say RF C1. Now this is equal to ZF. Okay. And ZF will what? ZF will be your parallel combination. This one parallel combination means what? RF into XC, RF plus XC, that is RF 1 upon j omega C. Okay. RF plus 1 upon j omega C. And if you solve this one, j omega C cancel. This is RF 1 plus j omega c RF ZF. Okay. So now my V naught will become here. V naught will become here minus ZF upon R, and here V input, that is my gain of frequency. Okay. So now if you put the value of ZF here, this will become minus RF by R, this R, upon 1 plus j omega c RF, C1 RF. So always consider the capacitor which is connected to the resistance. Okay. Now calculate the gain. So whenever frequency is high, this ZF becomes 0. Okay. Frequency is infinite, this ZF becomes 0, ZF becomes 0, the gain becomes 0. Okay. What is the meaning? If omega tends to infinite, ZF becomes 0. So gain becomes 0. So this is again low pass filter. At 0 frequency, this is the gain. So I'm erasing this one. So at 0 frequency, okay, my gain is minus R by R. Again, I'm writing it is by AF or A0 or ADC. You can write ADC also, 0 frequency. So my expression of A omega will be minus also you can remove or keep minus, or minus you can keep. Okay, minus you can keep. So minus A naught, or say A naught. Okay, and this is 1 plus j omega c1 RF. This again I can write like A naught 1 plus j omega upon omega c, where omega c again defined by C1 RF, and the gain of the circuit is A naught 1 plus omega upon omega c square, which is low pass filter gain. Okay, wherever omega is down, this is up, this is low pass filter. When omega is down, omega c is up, that will be high pass filter. So 1 plus f upon fc square, this is low pass filter. And directly you can also check without solving this one also. Let me take example of now high pass filter. I'm erasing this one. So put the heading now, high pass filter. Okay, first we'll see in the non-inverting configuration. Non-inverting configuration, then we'll see in the inverting configuration. High pass filter. So this is now High pass filter means I am taking a non-inverting configuration. This is my R. This is my RF. Here I am taking V naught. Now the circuit is same. Only I will change the capacitor value, capacitor position and resistance value, resistance position. I will write this is my R1 and here I will apply V input and here I'll put this one. And this is now example of high pass filter. Directly you can check when the signal has a high frequency, say low frequency, say 0. If signal has a frequency low 0, capacitor is open. Capacitor for DC capacitor is open. Capacitor is XC is 1 by proportional to 1 by omega. Capacitor XC is proportional by, so this become infinite. XC become infinite. Implies XC is infinite. And XC is infinite means capacitor is open. Capacitor C is open. And in open, no voltage reaches here. So automatically V plus is 0. So this implies V plus 0 and V output is 1 plus R upon R. That is V plus, that is also 0. That is gain is also 0. Gain at 0 frequency is 0. This is direct check and now we'll derive the formula. We'll see what happens in the formula. So let me write now the gain formula. Gain formula is V naught 1 plus RF upon R, this one, and V plus. Okay. And V plus is this one, V plus is R1 upon R1. Say this is C1. R1 plus 1 upon J omega C1 series into V input. Okay. And this V plus will be what? This will be, if I take J, or let it be like this. I'll write this is R1, I will divide. So this become 1 plus 1 upon J omega C1 R1. And here is V input. This is my V plus. And now my gain will become what? Gain. That is V naught. Put the value, this one here, upon V input. This will be again 1 plus RF by R. 1 plus 1 by J omega C1 R1. And now the formula will become A omega will be what? A omega will be 1 plus RF by R, 1 plus 1 upon J omega C1. Sorry. This we can write minus J, okay, 1 by omega. This C1 R1 I'm defining as omega C upon omega. Okay, where omega C is what? Omega C I'm defining as a 1 upon C1, 1 upon C1, 1 upon R1. So the expression for gain is now simple, this one. and magnitude of gain will be 1 plus RF by R under root 1 plus omega square omega c square. Is that correct or I have a mistake? Omega is down. Omega is down. Omega is down. Omega is down. Now, if A omega is, now frequency is 0, this become infinite and this gain becomes 0. If frequency is infinite, this term becomes 0 and the gain becomes, at infinite frequency, gain becomes 1 plus RF upon R. Can you see? Yes. This is 1 plus RF by R. So also, if you want, you can express A omega. This is gain at infinite frequency. 1 plus RF by R is gain at frequency. And you can express this formula as a 1 minus J omega C by omega, or A infinite 1 minus J FC by F, and magnitude also, if you want, just a way of writing. If you don't want, you should not write. Okay. If you, so A infinite frequency gain, this is 1 plus omega upon omega c square.
It's omega c upon omega.
A infinite 1 plus fc by f का स्क्वायर. तो वो तो अगर हाई पास है लो पास है वो तो डायरेक्टली पता चल जाता है. ओके, you don't need to do so much effort. Just if they are just asking what is the low pass high pass, you can directly tell. Okay, how much time is remaining? So this expression now you should remember what is for high pass and high pass. This is down, low pass this omega is up. So this is a non-inverting configuration. Now quickly in 5 minutes we'll do it in inverting configuration also. So please do it. Then I will drop this one. Now calculation you understand now. It is very simple calculation. So that's why I didn't do AC, because AC, this is the AC calculation. Just you replace XC by 1 by J omega C, L by J omega L, that's it. That has become your AC. Everything remains same method. And now you should know some complex analysis, because complex number, whenever J is involved, you have a phase also, you have magnitude also, but those things you do in your mathematical physics. So I think you don't be having any problem. Now this high pass filter inverting configuration. Inverting. This is minus plus, put capacitor here, and RF will be remain here. Here you apply a V input, that is your R1, that is your C1. Now write the gain formula here again. You see, if it is DC, this open, and then this open, nothing is reaches. What happen if this is open? If it is infinite, this by R by V naught. If it is open, then it will be gain will be 0. So let us say I have to write the gain. Gain will be minus RF. Say this combination is Z1 or ZI. Z1 say Z1. So minus RF. Z1 is R1 plus 1 upon J omega C1. Okay. And this minus RF by R1 1 upon J omega C1 R1, and this is same expression RF by R 1 plus 1 minus J omega C by omega, or where omega C is 1 upon C1 R1. So A omega is minus RF upon R 1 minus J F upon FC upon F, and the gain. So I'm not discussing this much further because the same things are coming. Gain magnitude, magnitude means this minus will be removed. Okay, so no need to put it in the minus A infinite. This gain will be already removed. So this will be RF by R 1 plus FC upon F square. And this gain, we can write A infinite because 1 plus FC by F square. Because if is infinite, you have a, if infinite, you have a gain, magnitude of gain, put it magnitude, RF upon R. In the previous case also you put magnitude here. So then there will be no issue. Don't put minus, just put magnitude. So this is your low pass and high pass we have completed. Now tomorrow we'll see the band pass and band reject filter, and we'll see also all pass filter also we'll see tomorrow. Okay, so I'll stop here. Thank you.